Okay, good afternoon, everybody. Yeah, welcome to another series of the Numerical Analysis Research Cluster NARC seminar series for the month of October. And today's talk is going to be a very specialized numerical analysis topic, which I believe many of us will find very interesting. And today's talk will be given by no other person than Dr. Marcial. And the agenda is what we'll be having. So we'll start with the welcome address I'm giving now. Then I'll read a short citation of the presenter. Then the presenter will going to present his research for 40 minutes. Then we take some questions and answers, some interactive section. And if you have some problems or maybe you have some things that you want to discuss that we can share together, then we can share that before we leave. Okay? So, but while you are listening to this talk, if you check the chat box, I have put the website of the what they call it of the seminar series. You can I put it there, and the YouTube channel, so that you can watch some of the videos or find some talk that are interesting to you. You can take those talk and try to watch them again. And I'm sure after this presentation, the presenter will also give us his what they call it his slides for people that are interested in working in this research. So after this, I'll just take the citation of the presenter today. So the presenter today is going to be talking to us on PDEs on curved and non-smooth surfaces, a new framework and its numerical analysis, to be delivered by Dr. Marcial Nguemfouo of the Department of Mathematics, Faculty of Science, University of Yaounde, University of Yaounde, at the Laboratory of Analysis and Application, and is also affiliated to the Mathematical Oncology Initiative at the Medical Physics Laboratory in the United States in New York. He is a highly accomplished PhD mathematician with a core expertise in the analysis and numerical simulation of partial differential equations on surfaces and manifolds. His doctoral and postdoctoral research established a rigorous foundation in the finite element method for geometric operators, with a specific focus on the well-posedness and the numerical conditioning of the Laplace-Beltrami operator on complex geometries. This strong theoretical base is complemented by a proven ability to apply advanced mathematical techniques to solve complex real-world problems across diverse fields. His interdisciplinary research portfolio includes developing epidemiological model for public health, COVID-19, under 5 mortality, collaborating with leading oncology institutes on mathematical models of cancer, designing neural networks for financial strategy optimization, and applying network science to social and agricultural systems. He is proficient in Python, R, MATLAB, and other scientific softwares like Salome and Paraview. He has presented his research both locally and in international conferences around the world. I will now call on Dr. Marcial to give us his talk. You may now share the screen, sir. You may now share the screen, sir.
Yeah.
Can you try?
Yes, I'm trying.
Okay. And while he's trying to share his screen, you may just invite your friends, because this is a very, very important topic that I know that is not well taught in Africa. Thank you.
Are you getting me? Are you seeing
Yes.
my screen?
Yes, your screen is very excellent. Just present slideshow. Excellent. Thank you so much. We are on 40 minutes. Thank you.
Thank you for giving me the floor. I'm Marcial. I defended my PhD on 23 May 2025. I'm interested in pure and applied mathematics, particularly PDE on surface. Why PDE on surface? Because many real-world engineering, biological problems occur on surface. I'm from the University of Yaounde 1. Now I'm working with the Mathematical Oncology Initiative from the New York, where we try to apply the PDE model to a cancer modeling, particularly breast cancer. Our talk is outlined like this. We will start by some introduction and motivation and the theoretical foundation, the finite element method, the conditional number, which is the key element to ensure that the computational, the linear system is well posed and may give a good solution. We will give some numerical result. We conclude and give some future work. And at the end, we will just show a simple application in mathematical oncology. The Poisson problem is defined like this, where here we have the Laplacian. This gamma is a surface, the manifold, because the two-dimensional manifold is called a surface. Our surface don't have a boundary. It is why we need this compatibility condition to ensure that our problem exists and the solution is unique. This field has some physical application in fluid dynamics, biology, material science. In the curved surface, we have some mathematical challenges like curvature effects, the non-Euclidean geometry. Our surface is closed, no boundary condition, and this surface is not smooth, the corner and edge, and we face some challenge like singular system. When the system is singular, it is more technical and more complicated. We have some theoretical objective. We are going to extend the framework from curved, smooth to non-smooth manifold and establish the well-posedness of the Poisson problem on general surfaces, develop some calculus on Lipschitz manifold, like Stokes, Green, and Poincaré theorem, and some numerical result here, like condition number of finite element method on curved surface. We derive the sharp bounds and a comprehensive validation on smooth and on non-smooth surfaces. The key originality contribution are new theoretical framework for Lipschitz manifold, condition number for closed surface with curvature, numerical proof that non-smoothness doesn't hinder convergence, practical implementation with industrial scale meshes. Classical setting. This theory started by Duke in 1988 on C2 surface. Duke used some kind of coordinate, Fermi coordinate, that need the surface to be C2. After that, they define the operator of gamma. Since to solve the Poisson problem, we need the Laplace operator. On surface, the gradient is defined like this, what we call the tangential gradient. It's defined like this, where this n is a unique normal, and this gradient u is the classical gradient. After that, they define the tangential divergence like this, and the Laplace operator is defined like a composition of divergence with a gradient of a function u. And the mean curvature is defined like this, h. An example for unit sphere, the normal is given like this, and the mean curvature is 2, and the Laplace is defined like this. This is classical. Here we need some functional space and the variational formulation, because the finite element method is based on a variational formulation. This is L2 space that we know in the lecture. Here, gamma, the same space is defined on the manifold. This is known in the literature. This is H1 space is defined like this. In the introduction, I say that our surface don't have a boundary, so the solution exists up to additional constant. To ensure that we will have a uniqueness solution, we need to find that solution in the space with mean value. It is why our variational formulation is given like this. When we have u, we find some solution u in H1 dias such that we have this equality. And the well-posedness is based on Lax-Milgram theorem. The bilinear form is continuous and coexist via the Poincare inequality, and the linear form is continuous. This ensures that our problem admits a unique solution. They do start with a C2 surface. Since when we discretize the surface, it is no more regular. For example, we have here an example of smooth surface, where the surface is approximated. It is no more regular, since we have here some singularity point. The surface is no more regular. It is at least Lipschitz. It is why we point some inconsistency, like continuous surface gamma is C2, but the discrete problem needs to be posed on a non-smooth surface. No unified framework for that analysis done in the Duke theory. He lacks the unified framework for a continuous and a discrete setting. It is what motivated our research. What is Lipschitz manifold? The topological manifold with Lipschitz transition map. It is an intermediate between topological and differentiable manifold. The differentiation here is not everywhere, but almost everywhere through the Rademacher theorem. As an example of Lipschitz manifold, we have polyhedra, cube surfaces, triangulated surfaces. The Rademacher theorem states that any locally Lipschitz continuous function is differentiable everywhere, almost everywhere. Our extended framework, we define the tangent space for almost every x on our surface. We define a Sobolev space via weak derivative, the measurable and Lipschitz differential form, and the Riemannian metric and volume form also almost everywhere. Here is some calculus on Lipschitz manifold. On Lipschitz manifold, we have singular and regular point. In the regular point, the tangential space is defined like this. And here we have the weak derivative on a Lipschitz manifold for f in LP gamma, where our gamma in Lipschitz manifold is weakly differentiable if there exists a vector such that we have this equality for every Lipschitz function phi. This vectors is denoted like the gradient, tangential gradient of f. And the Sobolev space is given like this, where gamma is the Lipschitz manifold. The main theoretical contribution. So, to solve our problem, to derive the weak formulation in order to obtain the uniqueness solution, we need Stokes theorem on Lipschitz manifold. That will help us to derive the Green theorem, which is a key theorem to obtain our weak formulation. After that, we need the Poincaré inequality type to prove that the bilinear form is coexistent. After this foundation theorem, we prove that our bilinear form is continuous and coexistent, and that the linear form is continuous. This ensures that our Poisson problem on Lipschitz manifold admits a unique solution as stated in this theorem. Let gamma be a Lipschitz manifold. F lies in L2 tiers gamma. This is the space with mean value. Then the Poisson problem has the unique weak solution U satisfying this. This inequality means that the solution depends continually to data. This ensures the stability in the computational framework. Surface finite element method. The gamma H is the triangulated surface approximating gamma through Delaunay triangulation. We define the finite element space, which is the piecewise linear continuous function with zero means. We define here the nodal basic function phi IH with this relation. This makes our finite element matrix sparse. The assumption is that our gamma H needs to be in the neighborhood, including the tubular neighborhood of the initial function. And we have our discrete formulation like this, giving UH tilde in our piecewise linear continuous function space. The variational formulation is given like this relation. This leads to the linear system A delta gamma H X equal BH, where our A delta gamma H is our finite element matrix. Our matrix have some nice properties like symmetry. The matrix is symmetric, positive, semi-defining. The matrix is not defining. Why? Because the kernel has constant vectors, and our matrix is sparse. The kernel has constant vector means that the matrix is not inversible. consequence for linear algebra is that our system is singular, but consistent if BH has zero mean to ensure the uniqueness of solution. The solution is found in the quotient space and needs some specialized iterative solver, conjugate gradient with some projection, and the standard preconditional ILU may fail due to some singularity. The shape function gradient is calculated on a triangle like this. The more detail of all this is in my thesis and my papers that I can share with you at the end of this presentation. The condition number. What is the condition number? For the symmetric matrix like ours, the condition number is given like this, where this is a pseudo-inverse on the image of A, means that this matrix is not an invertible matrix. Is what we call pseudo-inverse in the image. Significance in numerical analysis, error amplification. In the numerical computational, when we solve a linear system, the error depends highly on conditional number. Here, since our matrix is not invertible, we need to use the iterative solver convergence that depend on a conditional number. Numerical stability. If the matrix is ill conditioning, means that it is not well conditioned. The rounding error are amplified. How? Based on the no result from Yaounde and Nguemfouo, we show that our conditional number scar like this in H -2. But we have some challenge in our case. Singularity plus curvature and the fact that the surface is closed. Our main theorem in conditional start like this. There exists a constant such that for any closed piecewise triangulated surface gamma, we have this inequality where HT is the diameter of a triangle. This is the area of triangle. This is the Poincaré constant on gamma H. N is the number of nodes. Our condition number scale like a Euclidean space. If we check here, it is here we have an H2, and down, since the area is H2, square is H4. All of this give H -2. The curvature effect capture via Poincaré constant. Mesh quality appear through aspect ratio, H squared T on the area of T. The proof outline is given in 5 points. The reference will show that the effing map all triangle into the reference triangle. We use some gradient transformation like this, and we prove some lower bound of the discrete bilinear form through the discrete Poincaré inequality and the reference element, and the upper bound estimate shape function gradient. Combining both inequality, we obtain our design result. Some numerical setup and software. The geometry computational framework. We use some geometry, and our geometry and meshing is created through some platform, Salome, through geometry module and SMECH module. Numerical computation use Python with CDMaths and Solver library, and linear algebra use PEPC. And our visualization is through ParaView for our numerical result. Since our simulation is run on Linux with gigabit RAM sequential computation, we apply our result on some test cases. The unit sphere, which is on smooth surface, and torus, which is a smooth surface too, and cube skin, which is a Lipschitz surface. We use conjugate gradient with ILU preconditioning. Convergence analysis. The problem here, our gamma is a unit sphere. We use this exact solution and obtain this order of convergence 1.96, which is excellently agreement with theoretical order of convergence H2, confirming optimal convergence on sphere. And our conditional, we test the conditional number on sphere and obtain the theoretical order of minus 1.96, which is close to the theoretical value of 2. Numerical measurement, how our conditional number is measured. We compute eigenvalues and we extract the maximum eigenvalue and the minimum eigenvalue on IMA, and we calculate the condition number using linear regression on log scale to obtain our result, which is excellent validation of theory. The cube thing is an example of Lipschitz manifold, since here we have some singularity on the surface. Using this this exact solution, we obtain this result. You see here, we clip the surface to ensure that everything is happening on the surface and not on inside the cube, just on the surface. Is what we show this result like this. We also have a theoretical and numerical order of convergence. In this case, we have 1.91, which is near optimal convergence. No degradation from non-smoothness. An additional validated case is the torus here. With radius, the higher radius is 1, the minor radius is 3. We parameterize our torus and obtain the Laplace-Beltrami operator on torus. We use this exact solution to obtain this result with a best order of convergence.
Excuse me, Doc.
Yes.
It's like you have share your screen. We can't see the screen.
Please, the screen is on. Don't interrupt the presenter, please. Please, thank you. Please go on, Dr. Marcial.
The screen is on, please. Prof, continue.
Yes. Okay, thank you. Why, as stated in the beginning, The PDE on surface have a lot of application. Let me show just an example here in cancer receptor dynamic. The geometry here, our geometry is just a synthetic cancer cell with Lipschitz features. And the PDE, I choose a steady state receptor dynamic. We have here a model and we apply a surface finite element to have this result. And here, the red zone here is the high concentration zone. This is a heterogeneous receptor distribution on cancer cell membrane. The impact on oncology is that the personalized medicine is possible. The drug design, optimal therapeutic strategy, the metastasis understanding can be studied via the couple with Bowles model. I extend it in a more complicated surface reaction diffusion system for membrane dynamic with initial condition where the variable U is an receptor density, V in signaling molecules, and D is the diffusion coefficient, and lambda in internalization rate. The reaction term, which is nonlinear here. The difference here is that it is nonlinear. R is nonlinear. RU defining like this is nonlinear. This I is also nonlinear. As we need to apply the finite element, we start by the weak formulation. The weak formulation is formulated like this. Here is a time-dependent problem. It is why we add some time interval, t likes 0t, like this, small t likes here. And the existence theorem under the Lipschitz continuity and growth condition on R. Under this condition, there exists a unique weak solution, U, in this space. Some key estimate for the weak solution is the energy estimate. For a detailed calculation, I can send to you because I have it in my paperwork. Seeing here, I cannot show all detail. And the regularity is obtained like this, with this condition for the initial condition in H1 gamma. This is the discrete weak form given like this. After this, we obtain a linear system given like this relation. And here we have some numerical solution where here is a surface and computational mesh. And here we have the receptor concentration, UXT. And here we have a finite element convergence. The L2 error, and the red is a H1 error. This is just a spectrum of the operator, the Laplace operator. This is an energy decay via some Lyapunov function. And this is just a nonlinear term. And here I plot some test function, the width formulation, and integration by part 2 is plotting here. This is just to show an example. The optimal convergence is given like this. An application in cancer modeling, the cancer self-membrane with receptor clustering. We have here the cell membrane with some receptor. and here a 3D membrane surface. And the biological interpretation is that receptor clustering affect drop bidding. The membrane curvature influence diffusion. Diffusion, yeah, because in the surface we have some curvature. The nonlinear reaction model cooperativity and external stimulus SXT in our model represents drops. The clinical relevance is that we can predict drop response variability and guide personalized dosing, explain resistant mechanism. Summary of contribution. Theoretical contribution, the Lipschitz manifold framework, comprehensive calculus on non-smooth surface, fundamental theorem, the Stokes theorem, Green, Poincaré, extended to Lipschitz setting, the well-posedness analysis, Poisson problem on general closed surface, and regularity theory. Some numerical contribution are condition number analysis, complete OH negative 2 bound for Laplace-Beltrami operator, convergence validation on smooth and non-smooth surface, implementation framework, robust computational tools for surface PDE, industrial scale problem resolution. Some future direction. The PDE on surface has a not future direction. Only on smooth surface, we have a not open problem. Enough open problem. We can target the higher order PDE and nonlinear equation or nonlinear or Lipschitz manifold. Yeah, we can find some literature in the case of C2, but the domain still open. The regularity theory, sharp result for specific geometry singularity, the mixed formulation, the Stokes and Navier-Stokes equation on non-smooth surface. Here, I start Stokes and Navier-Stokes mixed formulation using Thomas finite element method, but I have not yet done on non-smooth surface. Even just here in Darcy equation, Darcy-Forchmacher, and Darcy-Forchmacher-Brigman equation, we can apply the same theory, the Canhira equation, and the spectral theory. Here, the eigenvalue problem on Lipschitz domain. I recently submitted a paper on a P Laplacian, this one, not yet on the surface, it's just in an Euclidean surface, studying the bifurcation of eigenvalue from 0 and from infinity. And the paper is under review. Under review, we can extend that paper in the case of smooth surface, and then in the case of Lipschitz surface. We can explore advanced numerical computation like multi-grid and domain decomposition for singular system on surface. For domain decomposition, but I started this theory on Darcy-Forchman equation, adding the optimal mass transport theory and the entropy. Yeah, I add this both notion. I send a paper to my colleague, which is a strong guide on geometry. We can also explore the HP adaptative high order element on curved surfaces, parallel computing, error estimate, reliable a posterior error indicator with a lot industrial geometry that like a computer-aided design model with sharp features. Impact, mathematical foundation to a rigorous framework for non-smooth geometry, numerical analysis, computational mathematics, practical algorithm for industrial problem, interdisciplinarity brides, connect pure math with engineering application with a more complicated problem that we can solve on manifold. Some practical application in engineering float in complex geometry like Darcy equation, Navier-Stokes equation, Darcy-Forchman-Brickman. We can add a lot of things like optimal transport, optimal control, entropy, and they give a lot of application. In biophysics, the self-membranous modeling, protein interaction can be modeled with a PDE on a surface. And here, the domain is open with a large number of extensions. In material science, interface problem. The interface problem is very, very important in many domains, even in biophysics, in biology. Computer graphic, surface processing, like image processing is more practical on surface and geometric modeling. Some software are available. CDMath, SolverMath is an open source implementation built in Syria, in Paris-Saclay, where my second supervisor is working in fluid dynamics. He is an expert in fluid dynamics. Now, I'm a remote collaborator with a mathematical oncology initiative since 2023. Now, I would like to apply this theory on cancer modeling, particularly breast cancer. The model can be extended in every kind of cancer modeling for advanced study. Interdisciplinary approach, applying surface PDE framework to cancer modeling, as I said, clinical relevant from mathematical theory to potential therapeutic insight. Our Lipschitz manifold framework enable modeling realistic cancer cell morphology beyond idealized phase. Stable numerical simulation despite geometric complexity. Foundation for patient-specific computational oncology. As I say, I am open for a collaboration because in this domain, I start at least 5 papers. If I can have some collaborator, we can write a lot of paper in this domain. The future clinical application is drug transport optimization on irregular tumor surfaces, personalized treatment planning using patient self morphology. What can I say more? From mathematics to oncology, as I said before, and some immediate application, we need to go deeper in this breast cancer receptor density and clustering to study more the membranous curvature effect on diffusion, the drug binding kinetic, and the internalization and recycling rate, partial stratification by surface topology, drop combination optimization, and resistance mechanism identification. This is just an example. Here is an example of HRL2 plus breast cancer cell surface morphology. This is an example of receptor clustering. This is just a drop bidding, but it is not yet, the result is not yet smart. I'm still working on it. I took just this example to tell us that it is possible. And here we have a drop distribution profile. Here we have a drop distribution profile. Thank you for your kind attention, question and discussion. But here in appendix, we don't have some detail because this talk needs a lot of notion, differential geometry, pure analysis on PDE, finite element method, numerical analysis, and a lot of ingredients. It was not easy for me to try to contract it and present like this. Then, if you need some detail in each aspect of this presentation, I'm ready to share the document with you to encourage you to enter this domain. I encourage those who are doing PDE, numerical analysis on 3DE, to explore this domain. I can help everybody, every person, to start working in some project. Even if you have some student that can work in this direction, I will be very, very happy to collaborate, to work with the person. Then we have here some detail regarding the finite element method, computational performance. Thank you very much. Thank you very much. Thank you very much.
Wow. Thank you so much. I want to really thank you for your well-detailed, and it shows that you actually took time to prepare these slides, and it's a way you wanted to really encourage a lot of people to come to this field. I want to say thank you for honoring our invitation, and I'm sure that the participants and the audience enjoyed your talk. So, not just to waste much time, I'll now open the floor for some for few questions please, questions to enlighten us. This is not a time to waste our time. Questions that can enlighten, that can throw more light into what he has presented. We all know that numerical analysis of partial differential equation is a very, very scarce topic, even in universities in Africa, even especially Nigeria. In many schools, the numerics of partial differential equation is not always taught in detail. So this is an avenue for you to ask questions and for you to seek help. And it can direct us on where we can get materials and information on this. And of course, you have heard that it's also open to collaboration. Before the questions start, I think I just want, I've seen somebody yes, I've seen a very revered professor in Nigeria, Professor Ekwagari, here and I would like him to just maybe open the floor, just give us something, maybe like a word of encouragement, or you should just say something, then we can now start taking questions. If Professor Ekwagari can hear me, the floor is open for you, sir. Is Prof here with us, sir?
He has left.
Oh, he has, but he's still online. Okay, maybe he has left. Okay, all right. So, in the absence of Prof, maybe we just take some few questions. Please just click on that react button and raise up your hands. Please don't interject anybody. Just raise up your hands and I will call you. Use the react button on the what they call it, on the Zoom platform. Go to choose react and open and raise up your hands, and I will call you. Okay, Dr. Diko. Are you raising up your hands or you're clapping? Okay, you're clapping.
I'm raising up my hand, sir.
Oh, okay. Please ask your question, sir.
Yes, I want to appreciate the organizers for this invite and also the guest speaker for such quite elaborate work, because when it started and by the time it's ending, I was just thinking on the kind of knowledge, vast knowledge you need that was coupled together to form the ideas in this work. It's a great one. Thank you, Prof, for the great talk. Yes, a number of things that I have in mind. Although the presentation for me was sketchy, I would have loved a more elaborate kind of mathematics to see the connections, particularly the theory connecting the numerical computation and the results. Because there are about three different things. First is the formulation of the theory as it's generalizing. Then came the numerical aspect where he had to do computations. Then those graphs that came up, could have shown more. So I would love him to send us the talk and the paper, because I can see that the references I was looking at, maybe I was going to see references. I saw maybe they are much more in the paper. Now, the kind of operators you use, for example, you mentioned, or I see in the slide, what you call a lifting operator. Now, when you are constructing such new results, some of these things require some explicit forms that one will be able to follow. So I want to understand what a lifting operator looks like in this concept, in the way you have described it. Then also, when I was looking at the computational methods that you use Python, you use other forms. Yes, it is lovely to see how you combine them, because they are all from different ends, although they are open source. So do you have to go and compute the matrix computation? Maybe in CD solver, brought it to Python or something. So those things would have really helped, particularly some of us who will be interested in understanding the work and looking at what to do with it. So then, did you use data like the cancer the last question? Did you have a set of a set of data that you use that combined with the numerical methods that gave those explicit interpretations? Thank you very much, sir. Thank you, Prof.
Thank you for your question. In my thesis dissertation, I have a lot of data from numerical, from theory. I start from a C2 surface, I move to the Lipschitz one. I can put explicitly the matrix coefficient, and I use the matrix coefficient to write a Python code. And in my thesis, I have all that Python code that you can use to obtain the same result like me. Concerning the cancer, I have not yet used a real-world data, but in the US, they use the bioportal, where they have all kind of data. This is just an example with a synthetic data that I use to show that it is possible to apply this research.
Thank
But
you.
okay. I will send you all document, please. You email me. We send you all
I will send you. I will request for those things through an email, and I will send to everybody by tomorrow.
Hello.
All right.
Okay, so Mr. Samson Ayo, you have a question?
Yes, thank you very
Okay.
much.
Yes, please.
First of all, I want to say thank you to the organizers. I saw this link on LinkedIn and I sent a follow request to Dr. Julius, and this is my first time actually attending one of these seminars. Also, thank you to the presenter for your presentation. There was a lot of rigor in your thesis, and I thank you for that. I had a few questions about your method, just motivations, really. I saw in your presentation that you said you use a conjugate gradient method for solving the linear system. Is that correct?
Yes.
Yes. And so my understanding of conjugate gradient is we're using for symmetric systems. And so in your preconditioning, you mentioned that you used an ILU preconditioner. So I was wondering what your motivation, why you chose that specific preconditioner, because if a system is symmetric, I don't know if it's symmetric positive definite, but for many symmetric systems, most people prefer to use like a Cholesky factorization for preconditioning or LDLT. I was kind of wondering why you chose to use ILU in your case. Thank you.
In our case, the ILU preconditional failed. To make computation, I use a script law, some kind of linear algebra technique to have the result here. Because when the system is not, the matrix is not inversible, we have two methods. We can use CG, conjugate gradient method, with some projection. We project in the space of μ0. But I can share the algorithm with you, point by point, how it is solved. But in perspective, I said, we target to explore the more advanced preconditioner to solve this kind of problem.
Okay,
thanks very much.
So if you need the materials directly to your email, now if you visit our website, there's a place where you can fill there's a form you can fill so that you'll be among those that will get regular emails from us. And by tomorrow, I will send an email with all the materials that Dr. Marcial will be sending to me. At this point, maybe I don't know if I think I saw that Professor Kagari has come back. Is Professor Kagari with us here? Oh, he's not here. Okay, Professor Aish Moju, could you just say something? Left. Professor Kagari, are you there? Yes, left. Okay. Who is on? Somebody's raising up his hands. Who is that? Okay, Dr.
Yes, I have.
Yes, please.
Okay. Good afternoon, everyone.
Good afternoon, Professor.
Okay, you are
yeah.
on, Dr. Bolani, you are on.
Okay, thank you very much. Yeah. I want to say thank you to the presenter, Dr. Marcial, for this insightful talk at this time. It's very explicit, and I think it's a very good one, and people who are working in the analysis of partial differential equation, numerical analysis, will take advantage of this. So in order not to waste time, I want to ask some questions, like the way you presented.
Yes.
Okay. Yeah. You talk more about the Lipschitz surface, and the way I want to see it, I feel that working on smooth surface will be simpler than this, maybe. So that is one. I want you to just maybe working with smooth surface will be like a sphere, for instance. It's a smooth surface.
Yes.
Okay.
Yes.
I feel that because of the smoothness, so maybe it will be easier. I want you to just enlighten us. Then the effect of curvature, you mentioned it at the beginning. So I want to see how does curvature affect your discretization and some other method you use. Because I was thinking that the way you will handle negatively curved surface will be different from the way you will handle the positively curved surface. So I want to see maybe if it's something that can be explained in a brief way now. So just to let us know, because the fear that we always have when we are talking about this type of geometry is curvature. So, and you see when something is not flat, you know, you are talking about non-Euclidean. Curvature will always affect, and the discretization may be difficult, more difficult than when you are working on a flat surface. So we want just yeah. Then the third question that I have is maybe somebody asked about motivation now. I want to see what is the motivation or the connection between these surveys, to choose these surveys as a space to model cancer. Because what I see that what other people do in modeling, you know, you just look on the in one dimension. If you want to go to
the differential equation, just
if you want to go to PDE, you just want to see maybe in a flat space. Maybe you just have x 2 coordinates system and you are fine. So what is the connection between this surface and cancer, and perhaps if it can be extend to other epidemiology phenomena that where one can apply PDEs? Thank you. That's my questions.
Thank you for your question. Solving on when we are on the C2 surface, Duke start the pioneer in the domain use what we call I call it Fermi coordinate. I just don't know if I can share my screen again.
Yes, you can. Yes, you can.
Okay, to discretize the surface, we use this Fermi coordinate. This is some global coordinate because we know the manifold don't have a global coordinate. Locally, we can define some system of coordinate to make calculation. The pure author in this domain define this kind of Fermi coordinate which is used to handle the discretization. Firstly, when I have my surface, I discretize such a way that the nodes of discretization belong to a surface. When I have my surface, the node of discretization belongs to a surface. After that, you can form the triangle through the Delaunay triangulation. Because in the numerical simulation, when the triangle are skinny, they can cause the instability. But to have the good type of triangulation, they use Delaunay triangulation, which make a triangle at this equilateral to avoid some skinny triangulation. Then the theory is based on this Fermi coordinate for a surface. And they define the leaf operator to exchange triangle. When I'm on a discrete surface, the operator is defined. And we use this definition to prove the convergence theorem. This A epsilon, I don't know if you remember the tubular neighborhood. When I have my manifold, I can define the tubular neighborhood like this. It is some open set that contains the surface. Now, with that Fermi coordinate, we can project the surface in that neighborhood. For example, the open subset of R3, we define a point inside the tubular neighborhood and we project it on the surface through an operator, and we show that there is an bijection from the point X on the tubular neighborhood and the projected point. After that, we prove that the discrete surface and the smooth surface are close. We show the convergence. The distance between both is less than C H2, which is going to 0 when H is going to 0. But it is very, very technical. But I have a lot thing to prove that. I can explain more.
Dr. Marcial, so tomorrow I'll send you an email. All the materials that you feel will be helpful for us, you just send to me back. Okay?
All right.
Then I'll just allow you to take this last question because we have spent more than 1 hour. We normally spend 1 hour. I'll just ask you to quickly answer this last one. I'm sorry. Dr. or Professor Akere Male.
Yes.
Thank you. Thank you.
Just make it very brief, please. Very brief.
Okay. Thank you. Dr. Marcial, thank you for the wonderful presentation. I will not bother you much because I believe since the email will be given to us, I have a lot of questions for you, but I believe through our chat or through mail, I can ask some of those questions. But majorly, quickly, I just want to ask, what happens if the surface is coarse? Because you talked about smooth surface, and I know from my experience of finite element method, you said that the surface is coarse or smooth. That is the first question. Then the second question is, what happened? Because you only talked about finite element. What happened if the surface has some region or has a particular region that has high gradient? How do you tackle such problem? These are the two questions. But I know I have a lot of questions because this is my area of research. I've actually done some things in finite element method, and I'm be looking for someone like you that can collaborate with so that we can do more. And thank God that you came on board. So probably maybe if you can answer these two questions, then other questions through your mail, I can forward mail to you. Then we can continue.
Dr. Marcel, before you answer this, maybe I just allow one person answer one more. So I just answer the two together. Okay, this last question. My friend, Dr. Chinedu, please ask your question.
Okay. Thank you very much.
Please make it brief, I beg.
Yeah, I'm going straight to the point. Thank you. So my question is the PDE on the surface. One of the slides you opened there showed the operator, the definition of the operator as in terms of partial derivatives, non-partial derivatives. So my question is, can I view this problem as a normal PDE problem? Because if I use that definition of the operator and put into those PDEs which you put, it will be like a normal partial differential equation. Would that be correct?
Oh, I'm not getting you well, dear Professor.
So what I mean is the operator you have the Laplacian operator on the surface, it has a definition. For the one I saw in one of your slides where you define it for a sphere. So, and the definition is in terms of some partial derivatives. And that's what I'm saying, that if I take that definition and substitute it into the PDE which you wrote there on the surface, it will just look like a normal partial derivative. And I'm asking that if one now or using the normal machinery or normal infrastructure for normal PDEs, would that be a different misconception?
I'm not getting you well, dear Professor. define on Lipschitz manifold or?
Okay, maybe can you just type on the chat box, Dr.
Please, on the chat box, if possible.
No, don't worry. I'll chat him later. I'll chat him later.
Okay, thank you. Thank you. Okay, Dr. Marcial, quickly, that last question. Can you remember again?
Can
you remember again the last question?
The last question, when we say if the problem is easy on regular surface.
Yes. Talking about
even I said even on regular surface there are enough challenge. The problem is that what we was working, we remarked that when the surface is discretized, we obtain a triangulated surface, which is no more regular. It is Lipschitz and not regular, since the theory based on C2 surface can no more be applied on a Lipschitz framework. It is what motivates us to move to a Lipschitz manifold, where we generalize the theory now. So the existent theorem can happen now on Lipschitz domain in general. It's why motivated to do that. So we have a Poincaré inequality in the Lipschitz surface, the triangulated surface. We have a Stokes and Green theorem, all that ingredient to do analysis now on surface.
It's
what motivated. Since on the surface there are a lot of problems, a lot of open problems, I say.
Thank you so much, Dr. Marcial. Okay, at this stage,
I'm not yet a great expert. It's just that I was very, very motivated by this domain.
Oh, thank you.
So I start by a geometry, after geometry analysis. After analysis, I start numerical analysis.
Yeah. Okay,
I'm still
so
working on it. I think if we collaborate, we can do a higher thing, a wonderful thing.
Yeah.
In Africa.
Okay, Dr. Marcial.
Yes, my dear.
Thank you. Thank you. Dr. Demba, are you there?
Yes,
Dr. Demba, are you with us?
Yes,
hello.
Yes, please, can you give us a vote of thanks? A vote of thanks for this, please.
So, Prof, I really appreciate your nice presentation. Yeah, thank you so much for the efforts you made. And to our audience, we also thank you. Thank you all.
Thank you very much, everybody, for coming for this. And
thank you very much, Dr. Marcial.
And next month, we'll meet next month to also discuss from another interesting speaker. And by tomorrow, I'll get all the materials from Dr. Marcial. And I'm sure Dr. Marcial will be willing to also, contribute more to this topic in Africa. Thank you, everybody, for coming for this talk. And I wish you,
Dr. Julius.
Yes, please.
And his email too.
Yes, everything I'll give tomorrow. Tomorrow I will send a message to everybody.
All right.
Yes,
all right.
Please. Thank you. And
thank you,
my friend.
Bye-bye. Thank you.
Dr. Demba.
Yeah, thank you, Prof.
Thank you, everybody.
Thank you all.
Yeah, bye.
Thank you so much.
Bye.